Hello and welcome. Thank you for watching this Flownex webinar where we will be modeling a typical power plant low pressure feed water heater. In this webinar we will highlight the capabilities of Flownex to model homogeneous two-phase flow. You will learn how to edit component properties, perform system design using the Flownex designer tool, and set up an action to alter properties in a transient solution with level tracking. The figure below illustrates a typical low pressure feed water heater. For this webinar we will only be looking at LP1, which comprises of a condensing section, in contrast with LP2 and LP3, which also include a drain subcooling zone. If we look more closely at LP1's geometry, we see the shell is a horizontal cylindrical vessel with a diameter of 2 meters and a length of 9.55 meters. There are two incoming flow branches to the LP heater shell, one carrying bleed steam, branch 1, and the second one distillate from the upstream LP heaters. Those are branch 2. Condensate from the condensate extraction pump flow through the tubes, branch 3, and the only exit branch is at the bottom of LP1, directly to the distillate pump, designated branch 4. There are 692 tubes in parallel, each with a length of 14.13 meters, a tube diameter of 25.4 millimeters, and a wall thickness of 0.75 millimeters. Here we can see the mass flows, pressures, and temperatures or qualities of each of the branches. The mass flows will be obtained using the designer tool in Flownex, but you'll get a better understanding of this later on in the webinar. We can now start modeling. I've set up the distillate pump line already and assigned the pump a pump curve. We can view or edit the pump curve under the Charts and Lookup Tables tab in the Flownex library. Here we can see the characteristics of the pump. I'm now going to move on to specifying the geometry of the feed water drum. To do that, I'm going to click on this node, which is our feed water drum. Under geometry, I'm going to select specified. I can then specify the vessel shape to cylindrical horizontal, the volume as 30 cubic meters, the diameter as 2 meters, and we can also specify the volume fraction. This will enable us to specify a level for the drum. In other words, vapor and liquid phases are separated in this node. We can then specify a fraction for the extraction pump of 0. This means that the connection is made at the bottom of the drum and only liquid is extracted. We can now use the designer to design our feed water drum level. In order to do that, I go to Configuration and Designer Setup. I'm going to right click to create a new designer configuration. I'll name it drum level. And then I'm going to drag the node level from the results tab of the node, and I'm going to drop it on under equality constraints. I'm going to select the target value as 0.15 meters, and what we're going to change in order to get that level is the quality. So I'll click on quality, and we're going to add a minimum and maximum value here. I'll leave the minimum 0 and I'll have the maximum set as 0.01. I'll set the configuration as active, and I can now run the designer. I can check if the designer converged. The designer has found a solution. So if I go to the results tab of our node, I can see that we have the desired level of 0.15 meters and a quality of 0.007674. We're now going to model the bleed steam into the feed water drum and use a restrictor with discharge coefficient component in Flownex to model a valve. I'm going to select the restrictor with discharge coefficient from the component library in Flownex and drop it on the canvas. I'll then connect it to our Feedwater drum, and I'll add a boundary condition where we can specify the pressure and quality of the steam. I'll start by doing that. We have a pressure of 44.4 kPa and a quality of 0.972. For the restrictor, I will select a diameter as our cross-sectional option, and I'll specify a discharge coefficient of 1. I'm then going to use the designer again. In order to design for a mass flow of 24.305. So we will add a new designer configuration, and I'll call it steam valve. I can then select the mass flow from the results tab of the restrictor, and our target value is a mass flow of 24.305 kilograms per second. And from the inputs tab, I'm going to select the diameter as our independent variable, and I will vary that from 0.5 to 1 meter. I will set this designer configuration as active, and now we can run the designer. I'll check to see if it's converged. It did. From the results tab, we can see we have a mass flow of 24.305 kilograms per second into the Feedwater drum. As we did for the bleed steam, we will design a valve to ensure a mass flow of 38.554 kilograms per second for the distillate coming from LP2. I'm going to use a restrictor with discharge coefficient and a boundary condition. We will specify a pressure of 126.3 kPa and a temperature of 79.2 degrees Celsius. We'll select diameter at cross-sectional option for the restrictor, and we'll specify a discharge coefficient of 1. I'm now going to set up a designer configuration again. I will call it distillate valve. For the equality constraint, I'm going to use mass flow. We have a target value of 38.554 kilograms per second, and I will vary the input diameter between 0 and 0.5 meters. I'll now set it as active and run the designer. We can see the designer converged, and we have our desired mass flow of 38.554 kilograms per second. We can now analyze the Feedwater drum results. Because we've specified the pressure and the quality on the Feedwater drum node, Flownex will create mass and energy sources in order to balance the network. If we look at the results tab of the Feedwater drum node, we will see that the mass source is effectively zero. It's very small, but this could be due to inaccuracies in the pump curve. The energy source, however, is quite large. It's 55,000 kilowatts. This is the outflow of energy required at the node to keep the level constant at the specified quality, thus obtaining energy balance for the node. And this is essentially the amount of energy that will be removed by the feed water flowing through the Feedwater heater tubes. I'll now start to create the Feedwater heater tubes. I'm going to drop a pipe element on the canvas. And a boundary condition. I'll specify the boundary conditions. We have a pressure of 1905 kPa and a temperature of 34.3. I'm now going to specify the pipe inputs. We have a wall thickness of 0.75 millimeters. Length of 14.3 meters. A diameter of 25.4 millimeters. A roughness of 40 micrometers, and we'll specify the number of increments as 5 and the number in parallel as 692. We will use the designer at a later stage to determine the loss coefficient to give the desired mass flow. I'm now going to design the heat transfer element to the Feedwater heater tubes. Under conduction areas, I will use the downstream pipe areas. I'm going to add a material layer. We have a thickness in the element direction of 0.75 millimeters. And we have a number of nodes as 2. The number of nodes divides the material layer into sections. Under capacitance, I'm going to specify 1000 and the conductivity 100. Upstream, I'm going to specify convection. Upstream in this case is the outside of the Feedwater heater tubes. And I'm going to specify a constant H as 14,000. Downstream, I'm going to specify convection as well. Downstream in this case is the inside of the Feedwater heater tubes, and I'm going to allow Flownex to calculate the H. We will now use the designer to design the upstream heat transfer coefficient and the flow loss coefficient inside the tube. This can be done simultaneously. I'm going to go to this designer setup. I'm going to add a designer configuration and call it Feedwater Heater. From the heat transfer inputs tab, I can drag the convection coefficient to the independent variables. We're going to vary this between 8,000 and 20,000. and the target value is going to be the energy source of the drum. We want that to be 0. From the pipe, I'm going to take the total mass flow from the results tab and drop it under equality constraints. We have a target value of 345.984, and our independent variable is going to be the losses. We will vary this from 5 to 20. It's set as active and run the designer. I can see that the designer found a solution, and we can double check. We have our desired total mass flow of 345.98, and the energy source on the node is 0. We can now analyze the Feedwater Heater transient behavior. The transient solution enables the user to change the simulation inputs in order to simulate the system response over a period of time. In order to set up and solve the solution steady state, we fix the pressure and quality on the nodes with level tracking. In the transient solution, we will remove the pressure and quality boundary conditions in order to allow the pressure and level to change at the Feedwater Heater drum. Before I run the transient simulation, I'm going to save a snap of the steady state solution. Snap is basically just a record of all the input values that can be loaded again at a later stage. I'm going to call the snap snap1. I will now create some transient events by setting up actions. To do this, I'll go to Action Setup. I will add a scenario, and I'll call it Feedwater Heater. We want to release the boundary conditions on the Feedwater drum. To do this, I'll click on the boundary conditions and I'll drag them over to the scenario. Here we can specify the trigger. So at 0 seconds, I want the pressure value to be not specified, and I'll do the same for the quality. And then at 60 seconds, we want the temperature of the feed water to dramatically increase from 34 degrees Celsius to 40 degrees Celsius. So I can do that as well by clicking on this boundary condition, dragging over the temperature. Under trigger, we'll specify the start time as 60 seconds. And we want the value to change to 40 degrees Celsius. I'll make sure the scenario is set as active, and now I can run my transient simulation. We can see that for the first 60 seconds the drum level and the pressure remained basically constant, and after 60 seconds, when we changed the feed water inlet temperature, we saw a change in level and pressure of the feed water drum.